All right, so we saw that changes in concentration can shift the equilibrium, and then our reaction is going to react to basically oppose that change. However, with gases, we can actually change the value of our Q without changing or directly changing the concentrations. We can do it by just changing the pressure. So remember that gases follow PV equals nRT, and we can reorganize this to say NV is equal to P over RT. NV is just moles over volume, so it's essentially equal to molarity, which is concentration, which will then be equal to PRT. So as we increase the pressure, we increase the concentration of our gases, and that makes sense. When we squeeze our stuff harder, we increase their concentration. So let's see how this is going to have an effect on our equilibrium and what Le Chatelier's principle is going to tell us. So for example, we have two NO gases decomposing into two NOs and one O2 gas, right? And so if we were writing the Kp expression of this, it'd be P NO squared times PO2, right? Products to their coefficients over the reactants to their coefficients, so NO2 squared. And so if we look at this top one, it's, if we combine the powers, it's to the third power. Whereas the denominator here is only to the second power. And so let's just take an example. We're just going to plug in some numbers and see what happens when we affect the pressure. So let's say that Kp is equal to 2, and that all of our pressures are equal to 2 as well, just to make it simple. Right, so they're all equal to 2, and so then we can plug them in, see if we're at K. So we get 2 squared times 2 over 2 squared, right? If you plug that in your calculator, just think about it, we're equal to 2. And so since that is what our Kp is equal to, we are at equilibrium. And then we can ask, what happens when we double pressure? Another way is to saying that, or half volume. Right, pressure and volume are interrelated, so kind of doubling one is halving the other, so it ends up being the same thing, right? And so let's take a look at what happens to our K. We're going to assume that we're at Q. We're going to assume we're not at equilibrium. We'll see if we are. So if we double the pressure, we're going to double the concentration. Or if you half the volume, you're going to double the concentration. So now we get 4 squared times 4 over 4 squared, right? You can plug that in your calculator, or you can just think these guys cancel out. And now we're equal to 4. 4 is not our value of K, so we are not at equilibrium. Right? And why did this happen? It's again because of these powers over here. Right? This is combined to the third power. This is to the bottom is to the second power. So one of them is going to grow faster, right? If you double, 2 cubed is greater than 2 squared type of thing, right? So this top numerator is going to grow faster than the denominator. So even though we're doubling the pressure of all gases, doubling the concentration of all gases, it's not having an equal effect on the products and the reactants due to these powers, right? Whichever one's to the highest power is going to grow faster. And so in this case example, Q is greater than K. And so that means that we have too many products. So because Q is products over reactants. So in order to get back to equilibrium, some of our products will turn into reactants, right? And so you can think about different scenarios that you can have. If your stoichiometry is the same, for example, 1A in equilibrium with 1B, then your K is just going to be equal, P of B over P of A. These are both to the same power. And so messing with the pressure of the volume has no effect, because they will both grow or shrink at the same rate or the same amount, and so it ends up canceling each other out. If your stoichiometry says that the number of reactants are greater than the number of products, so for example, 2A going to 1B, then our K will be PB over PA squared, right? Now the denominator is going to grow faster than the numerator. And so when we increase the pressure here, the pressure or the concentration, the pressure of the reactants is going to go up faster. And then to kind of cancel that out, we will have to turn some of our reactants into products. Right, so some of our reactants will turn into products. And then let's see, use that one. And then we saw an example of what happens when the amount of products is greater than the amount of reactants, right? We're going to go the opposite way here. Products are going to turn into reactants. So you can think about it in terms of math. There's also kind of just, if you reason through it in your head, there's kind of an easier way to think about it. As we increase pressure / decrease volume, right? They're the same thing. We have less room for stuff. And so our reaction will proceed to the side with less stuff, and vice versa. So when you increase pressure, you're going to go to the side with less stuff. When you decrease pressure, you're going to go to the side with more stuff. And so you can think about it just kind of logically, or you can kind of think about through the math and through the powers of what's going on.